So thermal conductivity measurement techniques, say delivered from Melbourne today by myself, Dr. Graeme Beardsmore. I would like to acknowledge University of Melbourne and also Ozscope for funding the thermal conductivity measurement laboratory at the University of Melbourne and also contributing to my salary at the University of Melbourne. So thank you, Ozscope. So first up, if we want to measure thermal conductivity, it's a good idea to know what thermal conductivity is. So people on this line probably have some concept of thermal conductivity, but just to go over it again, just to clarify the concept before I launch into how to measure it, I will just sort of cover fairly briefly what is thermal conductivity. Then I'll talk about what are the particular challenges for measuring thermal conductivity and specifically talking about rocks in this talk. Thermal conductivity is obviously critically important for many fields of endeavor, engineering and electronics and all sorts of things. But we're all earth scientists, I imagine, and we're mostly concerned about the thermal conductivity of rocks. So that's what this talk is actually about. So I'll talk about measurement strategies, methods, and instruments, and then three particular families of instruments: optical scanning, divided bar, and line source and other transient techniques. I'll briefly touch on high temperature and high pressure measurements, but largely this talk will cover measurements at atmospheric temperatures and pressure. So laboratory, just regular laboratory type measurements. So I hate to bombard you with a little bit of maths right at the top, but here is the steady state heat flow equation that dictates how heat is transferred by conduction through the earth or through any medium for that matter. So we have in this equation a Q at the front, and that is the average heat flow in units, in SI units of watts per square meter. So a heat flux value is equal to the average thermal conductivity over a particular depth interval in the ground, in this instance, multiplied by a temperature gradient over the same interval. So the change in temperature, and if we're looking at depth here, so temperature T1 at one particular depth, temperature T2 deeper down. So there's a change in temperature over the relevant change in depth from depth 1 down to depth 2. So this Greek lambda with the line over it means the average of the thermal conductivity in all the materials through that depth interval. And over here in blue, we have internal heat generation over that same interval. So largely from radioactive decay of unstable isotopes. So if we put all those terms together, then the heat flow is equal to the average thermal conductivity times the temperature gradient over the same depth interval plus half of the cumulative input of internal heat being generated within that volume of rock over that same depth interval. So this talk is really interested in this term here, the average thermal conductivity over the depth interval, and more specifically looking at methods and tools we can use to measure, estimate, and determine the thermal conductivity over a given depth interval. Because it's relatively easy to measure temperature. We have things called thermometers. Many thermometers can actually fit down a borehole. So it's a relatively simple exercise if you have a borehole to lower a thermometer down to two different depths, get two different temperatures, and work out what the average temperature gradient is over that interval. It's a little more challenging to work out what the average thermal conductivity is over the same interval. So that's why this talk is going to delve into that particular issue. So here's a real world example of temperatures that have been measured in a borehole, in this case, a gas production borehole in the Cooper Basin in Central Australia. which was drilled down to about 3,100 meters depth. The temperature, the average surface temperature, is about 25 degrees Celsius. The temperature measured at the bottom of the bore was in excess of 150 degrees. It was about 175 degrees Celsius. So the average temperature gradient over that interval is simply the change in temperature, 150 degrees, divided by the depth interval, 3,100 meters. So the challenge for us, once we have that average gradient, is to determine or estimate what is the average thermal conductivity also over that same interval. It's say it was relatively simple to work out the average gradient, 48 degrees Celsius per kilometer. Working out the average thermal conductivity is a bit more challenging. But we need the conductivity in order to turn that gradient into a heat flow measurement. So what is this thermal conductivity that relates temperature gradient to heat flow? So the thermal conductivity of a material, a rock in this instance, is the ability of that material to move heat from one location to another without actual physical motion of the material. So we say heat flows through the material, and the ability of the material to allow that heat to flow, we call the thermal conductivity of the material. Now, a material can have different thermal conductivity in different directions. So it can be more conductive in one direction compared to another direction. So the thermal conductivity is not a scalar property of a rock. It's actually a tensor property. And to fully describe the thermal conductivity of a rock, we really should fully describe the three orthogonal tensor components of thermal conductivity to fully characterize any anisotropy of the rock. Now, in practice, we rarely do go to that effort, largely because it is an incredibly large effort to determine the full three-dimensional thermal conductivity tensor of a rock. So in practice, we typically only take a single thermal conductivity measurement, which characterizes the thermal conductivity either in a single direction through the rock, or the average, or it characterizes, depending on what method we're using, characterizes the average thermal conductivity from heat expanding radially from a heat source. So typically, we do not characterize the full three-dimensional anisotropic tensor of thermal conductivity, but we should be fully aware that rocks can be thermally anisotropic, and I would say generally are. Another characteristic of thermal conductivity is strongly affected by porosity and the type of fluid that is in the pores of the rock. Rock minerals tend to be more conductive than water. So the more water you have in the rock has a general it generally reduces the bulk thermal conductivity of the rock. And if the rock is not water saturated, but actually air saturated or saturated by another gas, CO2 or natural gas, then that can lower the bulk thermal conductivity of the rock even further. So thermal conductivity strongly affected by porosity and the characteristics of the fluid that actually are in the pores. Another complicating factor about thermal conductivity is that it is a function of temperature and pressure. More strongly temperature than pressure. Thermal conductivity tends to decrease with increasing temperature. So rocks become less able to conduct heat as they themselves heat up, which means if we measure a rock in a laboratory at 22 degrees Celsius, and that rock has come from 3 kilometers underground where the temperature is actually 150 degrees Celsius, then we need to apply some sort of correcting factor to relate the value we measured in the laboratory to the in situ temperature and pressure underground where the rock came from. I always use SI units when I'm measuring and relating thermal conductivity, and the SI units for thermal conductivity are watts per meter Kelvin. So watts per meter per Kelvin. So watts being a thermal power unit, meter being a distance, Kelvin being temperature. And so that combination of units describes how well a rock can carry heat. So just looking a little deeper into some of those issues about measuring thermal conductivity. Firstly, we're almost always really interested in what is the thermal conductivity of the rock in situ, where it naturally resides underground, under particular temperature, pressure conditions, with particular fluid components within the rock. But it's very challenging to actually measure thermal conductivity in situ. Even if you have a borehole intersecting the rock, getting a thermal conductivity measuring device into the borehole is far more challenging than just lowering a temperature probe into the borehole. So temperature gradient, relatively easy to get from a borehole. In situ temperature, in situ thermal conductivity, very challenging. So it's by and large rather impractical to measure thermal conductivity in situ, with the exception of shallow marine probes, which simply dig into the top few meters of the sea floor, and some of those probes, which I believe Rob Harris may be talking about in about 19 hours from now. Some of those probes you can measure thermal conductivity in situ, but by and large, we need to recover rock samples from the bore or get samples of the rock formations we're interested in, measure those thermal conductivity values in a laboratory, and then relate those measurements back to the natural in situ circumstances that we're interested in. So given that we have to recover samples of rock or identify and obtain samples of rock to make those measurements, that in itself can be challenging. If you have a cubic kilometer of granite and you want to characterize what's the thermal conductivity, and that granite sits 2 kilometers underground, hopefully you have some sort of core sample collected by a borehole that drilled into that granite. But that core sample will just be a few cubic centimeters, and we're hoping that few cubic centimeters is characteristic of a couple of cubic kilometers of material. So obviously the more samples we can get from the rock formation we're interested in, statistically, the measurements we make will become more and more reliable. But simply obtaining those representative samples in a condition that we can make measurements on, in a condition that we're confident represents the in situ conditions of that rock, is certainly an issue that need to think carefully about. And then once we have the samples, even if we're happy they fully characterize the material, the formation we're interested in, we then have to cut and polish and grind those samples typically to fit within a measurement device, and do that in a way that doesn't damage the sample or change its thermal properties before we measure it. So preparing samples is another issue, needs to be thought through carefully. And each measurement device, which I'll explain as we go through this talk, each measurement device tends to have its own way that samples need to be prepared, and different levels of preparation can be required for different instruments. The instruments themselves need to be accurate and precise to get accurate and precise measurements. The test environment generally needs to be thermally controlled, not precisely thermally controlled, but we don't want strong cold wind currents blowing through our thermal property test, because we're making subtle measurements of the flow of heat through a material, We don't want thermal disturbance happening in our test environment. So controlling the temperature and air movement through the test environment. Also need to think about that. I've already talked about anisotropy. If we are really interested in anisotropy, then the rock samples need to be prepared and measured in particular ways to characterize anisotropy. And then I've also talked about relating the laboratory measurement results back to the in situ conditions where that rock naturally resides and where we're really interested in. So correcting for temperature and pressure changes. And then putting all that together, getting some idea of just how accurate, how precise our interpreted thermal conductivities are. So quantifying the uncertainty given all these complicating factors through the process of obtaining and estimating and measuring thermal conductivity. So just looking at obtaining representative samples first, we typically measure thermal gradient over absolute minimum intervals of tens of meters and often up to thousands of meters of thickness. So if we characterize a thermal gradient over that broad thickness of rock formations, we also need to characterize the average thermal conductivity over that same interval of tens to thousands of meters. So what material might we have available to characterize the formations that a particular borehole has cut through? If we're very lucky, the borehole might have been 100% cored, and we might have core samples that we can draw on from each of the formations that the borehole intersected. If not, we might need to try and find some outcropping material nearby from the same formation and just assume or hope that that the outcrop characteristics are similar enough to the subsurface characteristics of the formation. Ideally, we have core. Core is generally the best material to work with for thermal conductivity measurements. Cuttings, so the drill grindings that return to the surface during the drilling program, a far worse second best to core, but if that's all we have, then we can still try to get thermal conductivity measurements from the cuttings of the formations that have been brought back to the surface. And if all else fails, maybe electrical well logs, we may be able to infer physical properties like thermal conductivity from the electrical responses recorded on well logs in the bore. So I would say in order of best to worst material to work with, core is best. Outcrop material, I would say second best. Cuttings, at least their physical samples, probably third best. And relying on well log interpretations, probably the least reliable way of estimating thermal conductivity. So statistically, it's if we do have core all the way through the borehole, then regular sampling down through the bore is quite a good statistical method to characterize the average thermal conductivity over the interval we're interested in. So if we have a temperature gradient, perhaps over a 500-meter interval, then collecting a core sample every 25 meters or so, and then measuring thermal conductivity at a single point every 25 meters down that 500-meter section can statistically can provide a statistically reliable estimate of thermal conductivity over that interval. Ideally, we have samples from the same bore where we have the thermal conductivity, the temperature gradient information from. If we don't have samples from the same bore, at least we should be seeking samples from the same rock formation. And if we can't access the same rock formation, then at least as close as possible to the lithology mix. So in order of preferable to least preferable, most to least preferable, samples from the actual same bore, samples from the same formation or samples from at least the same lithology to characterize the thermal conductivity. First and foremost, the samples we're after, we want to characterize the formation. So the samples should be typical of the formation. So if you have like a formation that looks like this, which is heavily mineralized in some parts, slightly less mineralized in other parts, if we were to take this sample, we need to ask ourselves, is this representative of the whole formation? Or is the more mineralized section more characteristic of the formation? Perhaps we should be taking many samples through here to try and characterize the formation. So we do need to think closely when we're selecting samples to characterize a formation. We do need to consider to what extent those samples do actually characterize the bulk properties of the formation. So the samples must be typical of the interval, and hopefully that the interval for which we have samples is typical of the entire formation. Obviously, if a bore has been drilled specifically to sample a mineralized zone, and that mineralized zone is just a small component of a much larger unmineralized formation, then it's very unlikely that these mineralized samples are going to characterize that larger unmineralized formation. So we do need to be thinking about that. So these are sort of what some real samples look like. So hand specimen samples, core samples, drill cutting samples. So with the right instruments, we can actually get thermal conductivity measurements from any of these sample types, but not every instrument can measure every sample type. So that's if you have a very well-appointed laboratory and have a selection of instruments for measuring thermal conductivity, then you can have also a selection of what sort of sample types you can measure. But if you're limited to just a single instrument type, then that is also likely to limit what sort of samples you can collect and measure. So once you've selected your samples, then need to prepare them. And as I just mentioned, different instruments require preparation in different ways. So some instruments require just a single flat surface. Some can take measurements of soft material by pressing a needle into that material. Other instruments, you can pack soft material into a holding cell and then make measurements that way with the material sort of tightly compacted into the cell. And if you have core, then most instruments can measure the thermal conductivity of core, but again, the core needs to be prepared in different ways. So one instrument might need two polished surfaces. Other instrument might be able to take a measurement just of a single polished surface. This sort of instrument, we would need to drill a small needle-sized hole into the core and insert the measuring needle to get a measurement. So typically speaking, the more material we have, the more likely it is to characterize the thermal properties of the bulk formation. So if you just had a single grain cutting here, very little we can do with that. I don't know any common instrument that can measure the thermal conductivity of just a single rock chip. So you really want more material, which gives greater flexibility in what instruments can be used and how many samples you can measure to get statistical correlation across the samples. So representation, so we're after quantity of material within reason. Representation, so that the material does represent the specimen and that specimen represents the formation. Water saturation, ideally we are measuring the sample in the laboratory with the same level of water saturation that sample naturally has in situ. And my typical first assumption is that most rocks in the ground are water saturated. So I would typically water saturated samples in the laboratory before measuring thermal conductivity on them. So measure thermal conductivity on fully water saturated samples. Orientation of the sample. If a sample is anisotropic, then it will it'll be important to know what direction you're measuring thermal conductivity, and ideally should be measuring thermal conductivity along the same axis that the temperature gradient has been measured if we're looking to turn temperature gradient into heat flow. So in a borehole with core collected, we tend to aim to get to measure the thermal conductivity along the axis of the core, so in that direction, because that's almost always the direction that we have temperature gradient information as well. So some instruments naturally measure thermal conductivity along a single axis. Other instruments like the needle probe measure thermal conductivity radially, and then perhaps we need to make some assumptions and corrections to infer the thermal conductivity along the axis. It's not going to turn off. So that's orientation, and every thermal conductivity measuring instrument relies on an assumption that there is very good thermal contact between the instrument and the sample being measured. So a rough surface for an instrument that requires a nice smooth polished surface, a rough surface will not give a good measurement result. So we need good thermal contact between the samples and the measuring instrument. So what's to think about? It's not necessarily a quick and easy process to measure thermal conductivity. So a few words on controlling the test environment. The instruments for measuring thermal conductivity all assume that heat is being conducted through the measuring sample by pure conduction. If there's any disturbance to the thermal conditions in the laboratory, and in particular if there are air currents blowing past or if there are sudden changes in temperature during a measurement, then that can induce advective transient effects and conduction and convection of heat. So we want to, as much as possible, aim for pure conduction during a measurement. So applying heat in one location and detecting the flow of the heat into the rock by pure conduction. So we want to minimize any risk that there's any convection or advection of heat or radiation of heat from the sample. So conduction is only one mode of heat transfer. As much as possible for a measurement, we want to ensure that is by far and away the dominant mode of heat transfer during a measurement. So we don't want any cold drafts or hot drafts or any drafts whatsoever blowing past the sample during a measurement. So still air is best. If we can insulate the sample from its surroundings, all the better. Thermally insulate the sample. So here's a divided bar instrument, and within the divider bar here, you can see foam insulation, which is actually wrapped around a sample in here. So that insulation is to thermally isolate the sample during a measurement. And it also has the effect, if that sample has been water saturated, to minimize the evaporative loss of water during a measurement as well. And on the outside of this divider bar, there are also secondary shields to stop air currents from blowing past. So we have a thermal shield and then also an air shield. So for quantifying anisotropy, we're it is up to 25 now. People are slowly creeping in.
You could do it. Sorry, David, I'm a very important visitor.
Exactly.
Could you please mute your microphones?
Really, this is long. Leave the numbers.
Hello.
Do you take this on? I trust you.
Please, can you please mute
We're
your
in this together,
microphones?
but you're always going to do everything.
Well, because basically, he's taking it over.
I'll take that as a no. Okay. Sorry, just taking a screenshot of names of people who are on the call. It's one of my responsibilities today. I'll pick up where I left off in a second. Okay. So quantifying anisotropy. So that core sample on the right, you see a very strong foliation dipping from the top right to the bottom left. Very likely that foliation, those preferred alignment of minerals, also instills a thermal conductivity anisotropy in the rock. And generally speaking, thermal conductivity tends to be higher in the direction along a foliation and lowest perpendicular to a foliation. So we should also always be thinking of the possibility of anisotropy, even if we don't really want to characterize it. We should be thinking that it's possible that a rock is anisotropic, and perhaps make notes during measurements that on the possibility of anisotropy. So always consider the possibility. Note the measurement direction, and if we were measuring this core, we would almost always measure thermal conductivity along the core axis, which cuts across the foliation at an angle of roughly 45 degrees in this example. So simply even making a note of the measurement direction relative to the foliation can be useful to interpret the results later on. If we really do want to fully characterize anisotropy, then that can be done, but samples need to be prepared in particular ways in order to do that. And then the final step, once we've selected the samples, prepared the samples, taken very carefully controlled measurements, considered the possibility of anisotropy, then we need to correct our measurements for in situ temperature and pressure conditions where we're really interested underground. So almost all measurements are typically made at ambient temperature and pressure in a laboratory. So then we need to correct those measurements for in situ conditions. And it's useful to know that as precise as within half a degree or so, what temperature were the samples measured at, what pressure were the samples measured at, so that then we can apply corrections following, for example, publications like this one from Ben Norden at GFZ Potsdam a few years back, where he and colleagues did measure many rocks at many different temperature and pressure conditions in the laboratory at GFZ Potsdam, and characterize typical relationships between temperature, pressure, and how much thermal conductivity will change with changing temperature and pressure for different rock types. In this example, sedimentary rocks, mafic rocks, felsic rocks. And you can see the downward slope on these lines says that thermal conductivity typically decreases with increasing temperature, but the rate of decrease changes from one rock type to another rock type. So knowing what sort of rock type, what the measurement temperature was, what the in situ temperature is, then using charts like this, published charts, we can apply approximate corrections for in situ conditions. And then take a stab once we publish that number or apply that number in some way, understanding just how uncertain that number really is, especially if we're using those thermal conductivity measurements to quantify heat flow, and then we publish those heat flow measurements, put those heat flow measurements in the global heat flow database, then we really need a good handle on just how reliable that heat flow is. And that's typically comes back to how reliable is our thermal conductivity estimate, which often goes back to how reliable was the measurement of thermal conductivity. So some of the uncertainties in the process can be quantified. Instrument precision and accuracy are typically stated by the instrument manufacturer. But then there are other things that are less easy to quantify and are far more sort of subjective, like the heterogeneity of the formation. If we're collecting a finite number of samples and measuring thermal conductivity, but the formation itself is highly heterogeneous, then what uncertainty comes from that heterogeneity? Just how representative were our samples? Sampling bias. It's not unusual for a sandstone shale interbedded formation. You might get good recovery of core in the sandstone parts of the formation, much less or no recovery of core from the shaly parts of the formation. So we may end up measuring much more sandstone than shale from the formation, simply because they're the samples that we have to work with. So we need to be aware of that sampling bias and how that affects our interpretation of the thermal conductivity of the whole formation. How well the samples have been preserved and prepared, and has that preservation and preparation damaged the sample and changed their thermal conductivity? Whether or not we've quantified anisotropy, generally not. So how is potential for anisotropy affect the uncertainty of our inferred thermal conductivity? And then what additional uncertainty has been introduced by applying temperature and pressure corrections. So when you add up all these, it can be quite some level of uncertainty in the overall estimate of thermal conductivity. So it's good to be open, transparent, and realistic about just how certain we are about the thermal conductivity. In general, though, statistically, the more measurements we can make, the more we can reduce the overall uncertainty if we're trying to characterize the properties of a particular formation. So the rest of the talk really going to be looking at 3 different families of techniques for making the physical measurements of thermal conductivity in a laboratory. These are the 3 techniques that are recommended by the International Society for Rock Mechanics, the ISRM. And in this publication, the ISRM suggested methods for determining thermal properties of rocks in laboratory tests at atmospheric pressure. It was a product of the International Heat Flow Commission in 2017, I think it was 2016. So this is the de facto standard recommended way to measure the thermal conductivity of rock material. So there is no ASTM standard or ISO standard for measuring rock thermal conductivity. So this is the de facto global standard. And this document recommends 3 different techniques. So divider bar technique, line source technique, and optical scanning technique. And so I'll step through each of those techniques, and particularly the theory underpinning the technique, the construction of the instrument itself, and how sample selection and preparation of material applies to each of the instruments, and point out the strengths and weaknesses of each instrument. No one instrument can measure everything. They all have their strengths and weaknesses. Ideally, you can pick and choose between instruments. Often you can't, though. So I'll start with the divided bar, actually, because it was really the first instrument to be developed for measuring thermal conductivity of rocks. It is arguably the simplest to understand, and I tend to advise that if you only have a choice of one instrument that can be applied across a broad range of different sorts of samples, then the divider bar is probably the most flexible tool for measuring thermal conductivity. So divider bar applies a planar heat source. So just looking at this close-up image over on the right, you can imagine a source of heat at the top of the image here, and by applying heat at the top of this stack of brass plates and rock sample, we force a flow of heat unidirectionally from the top of the instrument down to the bottom of the instrument. And at the bottom of the instrument is an active heat sink. So, a divider bar applies a known temperature differential. So we set the top plate at a particular temperature and the bottom plate at another temperature. So we know the total temperature drop across the instrument from top to bottom. And the thermal conductivity of the rock sample is derived as a ratio of the calibrated thermal properties of these thin slices of plastic material between the brass plates at the top and bottom. So we induce a flow of heat, a constant flow. That flow remains constant. The same amount of heat flows throughout the entire instrument from top to bottom, and the thermal conductivity of the sample can be determined as the ratio of the temperature drop across the brass versus the temperature drop across the sample. So putting that all into maths, we get the thermal conductivity of the sample. Lambda of sample is the thickness of the sample divided by the temperature drop across the sample, multiplied by this, which is really a calibration constant, which is determined by carefully calibrating the instrument, and then that calibration constant remains constant for the life of the instrument. And then this delta temperature across R1 and delta temperature across R2 is simply the temperature drop across the top sections of brass and the bottom sections of brass. So the measurement becomes a simple ratio of temperatures measured at 4 locations through the divider bar. The key features of divider bar are won't go through all of these items. The key features are really the flat planar surfaces at the top and bottom where the sample sits, and by definition, the sample itself then needs to have corresponding flat polished surfaces at the top and bottom to make good thermal contact with the divider bar. So an inflexible divider bar, the surfaces need to be exactly parallel. That's very hard to achieve in a lot of cases. So good divider bar will allow some pivoting of the top plate so that it can account for slight non-parallel surfaces. So the other key features need to be able to apply a small retaining pressure along the sample to ensure good thermal contact. And we need to be able to measure temperature at 4 points throughout the thermal stack. So above and below the thermal standard at the top and above and below the thermal standard at the bottom, which also gives the temperature across the sample itself. So they're really the key features of a divider bar. Divider bars can be very simple, sort of manually operated, measure temperature manually at each of these points, through to so much more sophisticated with digital loggers and precise temperature sensors embedded into the device. But the general principle of a divider bar remains the same, regardless of how sophisticated the actual device is. So divider bars suit solid core samples and hand specimens because the samples need to sit between the solid plates and have a retaining pressure on them to maintain that axial flow of heat from the heat source down to the heat sink. They suit good, solid, competent samples that can be cut and polished and held under pressure in a device like this. So solid core and hand specimens ideally. Saturated porous rocks, to the extent that those saturated porous rocks are strong enough to withstand the constraining pressure. Divider bars are actually reasonably good at determining thermal anisotropy, because if instead of making a disc-shaped sample, so if you can prepare a sample that's a cube, you can actually measure axial thermal conductivity along the three orthogonal axes of the cube. So, so in terms of characterizing thermal conductivity, the divided bar is generally okay. Divider bars are also used, or that the principle of divider bar also tends to underpin those instruments that are actually designed for high pressure and high temperature measurements in dedicated laboratories. So if you can imagine this part of the divider bar where the sample sits, if this was encased in a heat protective cell, and that cell could be heated up to 200, 300 degrees Celsius while retaining the sample and making the required temperature measurements through the stack, then that tends to be how high temperature and pressure measurements are made. So those instruments tend to follow the divided bar methodology. Divider bars can also measure specific heat capacity and by inference thermal diffusivity as well. But for this talk, we'll just focus on thermal conductivity. So preparing samples for the divided bar. My own laboratory methodology, if I get a single piece of core, I tend to try to get 3 samples from that one piece of core, so that at least I get a very minimal mean measurement and standard deviation across the 3 samples from the one piece of core. Generally, if we start with core, we cut discs from the core, grind and polish the surfaces, and then water saturate the sample. So samples can be prepared as discs if we have full diameter core. It can be prepared as prisms if we have split core, and if we're interested in thermal anisotropy, we can also prepare cubic samples that are polished on all 6 sides, so we can measure thermal conductivity along through 3 different orthogonal directions through the same sample, and in that way characterize the full anisotropy of the sample. Now, so the divider bar is an instrument that can also measure the thermal conductivity of rock chips, drilling chips, if those chips can be packed tightly into a retaining cell, and then the thermal properties of the entire cell can be measured in a divider bar, and then the influence of the cell itself can be mathematically removed to infer what are the properties, what's the thermal properties of the material inside the cell. So that's sort of shows the principle of sample preparation for divided bar. It's rather critical. The one critical component for preparing samples for divided bar is the surface flatness. The surfaces that make contact with the flat plates of divided bar, the sample surfaces must be flat. Polishing is not so critical, but flatness is. If you have slightly concave or convex surfaces on the samples, then that will very seriously, critically impact the thermal contact of the sample with the divider bar plate, and can have quite a dramatic effect on the inferred thermal conductivity. So surface flatness is the one critical feature of preparing samples for divider bar measurements. So the strengths of the divider bar as an instrument, so it's a planar heat source which applies heat flow, a known heat flow, in a uniaxial direction through a sample. It's quite versatile with respect to the sample type that can be measured. It gives a whole rock uniaxial measurement, which is typically what we want if we're doing heat flow work. So if we have a temperature gradient, we want to know the whole rock thermal conductivity in a uniaxial direction to turn that temperature gradient into a heat flow. And divider bars sort of give that whole rock uniaxial measurement on albeit small samples, but at least give us the thermal conductivity in the direction we're interested in on a hopefully statistically large enough sample to reduce the impact of just small grains in the sample. The method can be adapted for high temperature and pressure measurements, as I talked about already, and instrument can also measure specific heat capacity and diffusivity. So that's the strengths. The weaknesses is that the effort required to prepare the samples is far and away much more than for the other instrument types. So there's quite a lot of effort goes into simply preparing the sample for measurement. Making a measurement itself is quite quick and easy once the sample's prepared. It's preparing the sample is what takes the time for divider bar measurements. Measurement results are very sensitive to the flatness of the surface of the samples, like I just talked about. It's relatively slow in terms of measurement time. It might take 10 minutes to get a measurement in a divider bar for a single sample, whereas the other instruments I'll talk about might give a measurement in just a couple of minutes. Basically, it works on a limited volume of sample, as all the instruments do. And if all we have is soft cuttings packed into a cell, then it can actually be quite complex to interpret what the in situ thermal conductivity of a rock formation is if all we have is measurements on rock chips that came from that formation. So a few weaknesses there, some general specifications for a typical divided bar, and you can really design divided bars outside of these specifications, but typically for measuring rock thermal conductivities, we build divider bars with surface areas on the order of 25 to 65 millimeter diameter, which also imposes a limit on the size of the specimen that can be measured. So the limit on the specimen size is determined by the size of the bar, divider bar. The thickness of the specimen, typically we look at 1 to 3 centimeter thick, maybe up to 4 centimeters in some cases. They tend to measure thermal conductivity in the range 1 to 10, which covers most rock types. In fact, the vast majority of rock types. Some very metalliferous ores may exceed 10 at the higher end. Some very coal-rich or organic-rich materials may come in lower than 1 at the lower end, but typically rocks will fall in that 1 to 10 watts per meter Kelvin range. A well-designed, well-built thermal conductivity with well-prepared samples should give an accuracy within plus or minus 2% for core samples, and much less accurate, maybe within plus or minus 10% for cutting samples, and repeatability on the order of 1%. So repeat the same measurement on the same sample, you should get the same result to within about 1% for core anyway, maybe within 3% for cuttings. Divider bars do take time to warm up. The heating elements in them, you typically need to turn them on and wait about an hour before making the first measurements of the day. So that can impose a bit of limitations on throughput time. If you have lots of samples to measure, then you do have to factor in that warm-up time before you start work each day. But once you're going, you should fairly comfortably be able to measure 2 samples per hour, at least 2 samples per hour. And maximum sampling resolution. So you're getting 1 result per solid sample. So you're getting 1 thermal conductivity value per each about 30 millimeter of sample. The other instruments can be much finer resolution. So, but for divider bars, it's a fairly chunky 1 thermal conductivity measurement per several centimeters. and it's best to make the measurements under ambient conditions, plus or minus sort of 10 degrees. So, so that's divided bar. I'm going to jump now without a pause. Going for an hour already. We do need to speed up. You probably have all have other things to do. But so the divided bar applies a plane source of heat, and that plane of heat moves in a single uniaxial direction through the sample. The next family of measurement tools I'm going to look at is the line source family of tools. And as the name implies, this family of tools imposes a linear source of heat. So divided bar was a planar source of heat. The line source tools impose heat along a line, a linear wire, typically. And the tools control the heating rate within that wire. So they impose an electrical current through the wire. The electrical current makes the wire heat up. By measuring how much electricity is being pumped into the wire, that can tell us how much heat is being generated within the wire and conducting out into the surrounding sample being measured. So from a linear source, heat conducts in all possible directions that it can into the material around it. So if our linear heat source is embedded within a needle and the needle is embedded into the sample, then the heat from that needle will radiate out in all directions around the needle. So then we must infer the thermal conductivity of the material, and we do that by measuring the rate at which the temperature increases at some sensor point that's embedded in the needle itself. And just generally speaking, if a rock sample is more conductive, then the heat will dissipate faster. Temperature of the needle will increase slower. So if the needle warms up slowly, that means our sample is high conductivity. If the needle warms up quickly, that means the sample is low conductivity. And the mathematics of the diffusion of heat, the conduction of heat from the source can be solved for either a full space conduction or half space conduction, and different applications of this line source method have been developed for either full space or half space applications. So a typical line source instrument for measuring thermal conductivity will have a heater wire and a temperature sensor embedded in a needle or holder of some sort for a full space measurement, or a wire and a sensor embedded on the surface of a carbonate plate for a half space measurement. Then the other critical part of a line source instrument is that it needs a source of electricity, a controlled source of electricity to inject a known electrical power into the heater needle, and with the assumption that that electrical power converts to heat in the needle, and which tells us how much heat is being generated in the needle, and from that we can infer the how much heat is conducting out into the surrounding material. So this is just some images on the screen here. So this is a needle probe. And typically a needle probe like this will connect to a control box like this. This is a flat half space type probe where the heater wire is actually put on the surface of a flat polycarbonate disc, in this case, with a heater sensor, and then the flat disc is pressed against the sample for measuring conduction of heat into the half space. And this is a schematic diagram of one of these needle probes, and what is inside it is a heater coil and a little temperature sensor, effectively. So line source tools, probably the most prolific thermal conductivity measuring tools on the market are line source tools. If you Google thermal conductivity sensor, thermal conductivity measurement instrument, you'll come up with a plethora of these line source tools on the market. So, and they vary in the size of the probe. So long, thick probe, shorter, thinner probes. They vary in whether it's a needle probe or a wire on a flat surface for either a full space measurement or a half space measurement, and they vary in other ways as well, as scale being a major one. These are all laboratory scale, but needle probes, or the needle probe theory, is also good for scaling up to much larger scale. So needle probes tend to be best for measuring unconsolidated material, or more to the point, if you have to measure the thermal conductivity of unconsolidated material, needle probes are the best option for those measurements. Largely because you can press a needle quite easily into unconsolidated material, and then measure the conduction of heat from that needle out into the surrounding unconsolidated material. You can also measure solid materials though, and the half plane sensors are best for measuring the thermal conductivity of solid materials. Line source tools are also applied in situ measurements for marine probes, for example, like Rob Harris will talk about in about 18 hours time now. So if you can inject a probe several meters long, and within that probe inject it into the seafloor sediments, if you can also include a heating coil within that probe and some temperature sensors, you can apply current through that heating coil, measure the diffusion of heat out into the surrounding soft sediments, and infer the thermal conductivity of those sediments. So that's often employed in marine heat flow measurements. So the general process for preparing a sample for a line source measurement is to either pack loose material tightly around a needle, if it's a line source needle, or pack the loose material into a container if it's a half space type measurement. You can also make measurements on solid samples, in which case you just need a single polished flat surface large enough to hold the sensor. If you have a needle and soft material, you can press the needle directly into the soft material, so very little sample preparation really needed other than holding your soft material in some sort of container that allows you to press a needle into it. And you may or may not need to saturate the sample if you're looking at dry rock chips and you know that those rock chips sit in a fully saturated environment normally, you might want to make the measurement with those rock chips fully submerged and saturated in water. But it's critical to ensure good thermal contact between the heating wire and the sample. With a needle pressed into soft material, that's arguably much easier to do. With a half space sensor probe here, though, you need to sort of apply pressure to keep that heater needle on the sample surface, and may need some sort of contact paste as well, just to ensure good thermal contact. These things can scale up. Here's a Mexican-sized heat needle, we call it, which is about 1.1 meters long. It's got a heating coil in it and temperature sensors, and acts as one of these line source needle probe thermal conductivity measuring devices when this is injected into the soft soil, hammered into the soil. So this can make in situ thermal conductivity measurements in the top meter of soil. Line source, another strength, or one of the main strengths I already mentioned, is that it's fairly minimal sample preparation required. Generally a fairly rapid measurement. So at just a laboratory scale measurement with a short needle, you should be able to get a single measurement in just a couple of minutes. So faster than a divider bar. Far and away the best choice of tool for unconsolidated material, and scalable. So it can measure with a fairly short needle in the laboratory up to meter scale in this particular device. And the same concept is used in marine studies down to even as deep as 5 to 7 meters deep, characterizing thermal conductivity in the surface sediments of oceans. And this same concept has even been applied in much deeper boreholes with very large heating wires dangled hundreds, if not 1,000 meters into deep boreholes for in situ thermal conductivity measurements. Arguable just how successful those in situ thermal conductivity measurements really are, and they take a long time to complete, because as you scale up the size of these probes, the time required to get a measurement also scales. So you might get a measurement in the laboratory in a couple of minutes. This particular instrument takes an hour to get a thermal conductivity measurement, and if you scale up again to borehole type scale, you might need to run your heater coil for a week or 2 weeks to get a measurement. So the time required scales up along with the physical size. But really, at the end of the day, these line source type instruments are the only technique that are suitable for in situ measurements in the ground. So the weaknesses. So yes, several strengths for line source. The weaknesses, much harder to characterize anisotropy on a sample when the heat is conducting out radially from the needle source or the wire source. Understanding how thermal anisotropy might affect that conduction is much trickier. The mathematics becomes much more complicated than for a divided bar measuring along a single axis. Can be done, but much more time consuming to prepare samples and make measurements in different directions and crunch the numbers to assess thermal anisotropy. For the flat press surfaces, generally limited to a sample size at least 50 millimeters by 50 millimeters. So it's very hard to get a measurement on smaller samples with a line source tool. Very sensitive to the thermal contact with the sample surface, as already mentioned for the divided bar. All of these instruments, in fact, are sensitive to the degree of surface contact. And also, most of these sensor probes only have a single temperature sensor within them, and you're really just getting a thermal conductivity measurement in the close proximity of that temperature sensor. So a temperature sensor is really just a point, so a single point. If that single point of the temperature sensor happens to line up next to a particular dominant grain of rock in your sample, then the result is going to be dominated by the thermal conductivity of that single grain of rock. So that's a bit of a weakness. It's all right for homogeneous samples, but if the samples are heterogeneous, then the actual location of the temperature sensor within the needle can impact the result quite strongly. And if your aim is to characterize the thermal conductivity throughout a full profile of rock, then that actually can be quite time consuming, because you might get a single measurement in a few minutes, but you might need to repeat that measurement dozens of times or hundreds of times to fully characterize a rock profile. So strengths and weaknesses, as with every tool. So generally specifications, these also tend to measure in a particular range of thermal conductivities. So possibly better at the lower end of the thermal conductivity scale. Divider bars were good down to about 1 watt per meter Kelvin. Line source probes can push that down about another order of magnitude. So better for measuring lower thermal conductivity materials, which is good for unconsolidated material, organic rich materials. That's for the full needle probe that embeds fully into the material. So the half space, not quite as far down to the lower end, but still more so than divider bar. Accuracy, the manufacturers tend to quote 2%. That sounds about right. But got the similar accuracy to divider bar. Very small needles, the accuracy might be impacted a bit. Should be able to get a measurement for a normal laboratory scale needle in about 80 seconds. If you're going to repeat measurements at the same location, then you need to allow time for the heat to dissipate before starting a new measurement. So repeat measurements are a bit slower. Typical length of a needle, 70 millimeters. Diameter, 30 millimeters. That's not right. It should be 0.3 of a millimeter, might be a minimum diameter. The height is right there. And rock sample dimensions. Yeah. So now on to the third and final measurement family of measurement tools. So the divider bar was a plain source of heat. The line source, as its name implies, a line source of heat. The third family applies a point source of heat. So remove one more dimension again. So we've gone from line source, or we've gone from planar source to line source, now to point source. So the third family of tools exploits a point source of heat, and more particularly a point source of heat that moves at a constant velocity across a rock surface, and the heat generated by that point source conducts in 3 dimensions into the rock. And then there's a trailing temperature sensor that follows along behind the heat source, which measures the temperature effect of that heat source at a known distance and time behind the heat source and to the side of the heat source. And from those changes in temperature induced by the point source of heat, we can infer the effective thermal conductivity and even the effective thermal diffusivity of the measurement sample relative to reference standards, which will also be measured at the same time. So here's what one of these instruments looks like. Far fewer on the market. In fact, there are only 2 types on the market. There's really just a single manufacturer of this sort of instrument. The instrument itself was invented by Yuri Popov, who was a former chairman of the International Heat Flow Commission. So very respected man in the heat flow field. He actually invented this machine to detect cracks in rocks, believe it or not. But then quickly realized it's a way to measure thermal conductivity of rock samples. So the 2 types on the market. Type 1 can measure full diameter core and split core, so half core. Type 2 is really designed for measuring smaller samples, so core plugs and cuttings bigger than 8 millimeters thick, so not very fine cuttings, but sort of gravel or bigger size rock cuttings. So the 2 different types. You're very unlikely to buy both types because they're quite expensive instruments, but you do need to be aware of the limitations of the type that you might have or purchase. But both types, they employ the same components in their design. There's a heat source, there are infrared temperature sensors, there's a movable optical head that moves the heat source along the sample at a defined speed, and then there are reference standards that are measured during every measurement. So in the picture here, the measurement standards are these small white blocks at the start and end of this chain of samples, and these are the samples themselves. The heat source comes up from below within the metal screen area here, and the temperature sensor also comes up from below. So this is a type 1. Type 2 has the same components, but the heat source and sensor are mounted to the side, and the standards are again clamped sideways on this instrument at the start and end of the samples to be measured. So you'll notice that you can measure several samples at once, which is a big advantage. And another curious ability of this instrument is to take many scans at different points around a core and pretty much create a pseudo two-dimensional surface scan of the surface of the core. And here's an example that was run at Melbourne Uni several years ago, which clearly delineates the different thermal conductivity of these different lithological units in this sample of core. So something like it's about 24 different scan lines were run at regular intervals around the core, which clearly delineated the changing thermal conductivity of these different materials. So given that it's a very precise point source of heat aimed by a laser, it's very good for high resolution investigations of thermal conductivity. And you can't produce anything like this from a divider bar or a line source. So it's very good at very precise high resolution investigations of thermal conductivity. It's also a non-contact measurement. So of all the instruments for measuring thermal conductivity, this one is least sensitive to maintaining good thermal contact with the heat source, because the heat source is applied optically, and thermal contact is actually maintained by painting a black strip along the sample to ensure optimum absorption of the heat from the laser onto the sample. So it's very good for surface mapping of thermal properties. And you can create interesting images like this, which map the thermal conductivity of a core in pseudo 3 dimensions around the core surface. So minimum preparation needed. You don't need to cut or polish the surfaces. All you need to do is apply a black line along the surface for absorbing the optical scanning laser. Black line can be paint or even just black tape, as long as the black tape itself is making very, very good contact with the sample. Black electrical tape is often applied for these sorts of measurements. You can measure flat surfaces or minor curvature. Major curvature can be a bit of an issue, so we want pseudo flat surface or minor curvature. Strip of black tape or paint along the line to be scanned. And if you want to investigate anisotropy, you can actually scan in different directions, in 3 different directions through a sample like this. So along the axis, across the axis, and then on the perpendicular surface, you can get 3 scan lines with the optic scanner, and from the results of those 3 scan lines, infer thermal anisotropy. So the strengths of these sorts of systems are minimal sample preparation. It's a non-contact measurement, so you can borrow core and return the core in pretty much the same state at the end of the measurements. It's very rapid. The laser moves along the sample at centimeters or certainly millimeters per second, so you can scan several cores along a whole string of samples in a matter of a couple of minutes. Continuous high resolution, so millimeter resolution scale data generated can characterize thermal heterogeneity. If you have a heterogeneous sample, then because of the very high resolution measurements, this sort of instrument will characterize that heterogeneity, characterize thermal anisotropy by measuring in different directions, and sampling spatial resolution can be varied by varying the scan speed. So if you want higher resolution, you can slow down the scan speed. If you don't need such high resolution, you can speed it up and get through more samples in the same amount of time. The weaknesses, they're very expensive instruments. So last time I heard a quote, the cheapest ones were about 70,000 US dollars, I think. So say there's only a single manufacturer. That was several years ago. I'm not even certain that you can still buy them. I haven't contacted that manufacturer for a while. There's a number of these instruments in Australia, I'm aware. Melbourne Uni has one. I think Adelaide Uni has one. Maybe a third, Geoscience Australia may, although don't quote me on that. So they are available. Certainly the one at Melbourne Uni doesn't get a lot of use, and we'd be very happy for other people to use it. Interpreting the data is fairly computationally intensive. It's all handled by commercial software, so it's a bit of a black box, the interpretive software, but and it's software that runs on a fairly old Windows machine at the software that we have at Melbourne Uni, at least. So our biggest fear is that the machine running the software will crash and we won't be able to use it anymore. But again, one instrument cannot do everything. So if you have rock chips, if you have relatively small samples, then the type 1 instrument is not going to be able to measure those smaller samples. So it is very flexible, this machine, but still can't do everything. So it can't measure small rock chips, for example. Only operates under ambient laboratory conditions. There's no high temperature version of these laser scanner machines. And by doing a single scan along the axis of a core, that does not tell you the vertical thermal conductivity of the core. So the heat conducts into the sample in 3 dimensions from the point source. So it's not even just radially into the sample, it's actually conducting in 3 dimensions into the sample. So some fairly complicated maths is required to infer what the vertical thermal conductivity of the samples is if we're doing heat flow measurements. So I won't read through all these accuracy and precision values. I'll just pick out that again, like the other 2 recommended instruments, should be able to achieve accuracy on the order of about 2%, plus or minus 2%. And resolution on the same order. Repeatability should be on that same order of a few percent. Lots of numbers here about how many samples you should be able to get through in a day. The resolution, point resolution, maximum lengths of the dimensions. This is all general specifications for the instrument. So winding up now, an hour and a half. It's probably a record for talks I've given recently. So really there's a range of techniques out there for measuring thermal conductivity of rocks. So the 3 recommended techniques by the International Heat Flow Commission, the divided bar, which applies a planar source of heat, the line source, which applies heat along a single one-dimensional line, and the point source laser technique, which applies heat at a point. So at the end of the day, if we're doing heat flow work, we're really trying to characterize the thermal conductivity of a full volume of rock. So we need to be thinking through the whole process about sampling, rock preparation, choice of instruments, precision and accuracy of the measurements, minimizing errors along the way, and trying to build up just a holistic picture of the thermal conductivity of what are actually large volumes of rock in the ground. So the key points here are just be aware that there are a range of different techniques available out there. Each have their pros and cons. Each are better suited for one sort of sample type or another sample type, one sort of measurement requirement for another measurement requirement. Here at Melbourne Uni, we do have access to all 3 types of instruments. So we have, I'll give a plug to Ozscope, which maintains the instrument laboratory. Ozscope would love for these instruments to be used more. So if you have applications, you think you want thermal conductivity measurements of rocks done, then get in touch, and we'll happily lend our laboratory facilities to your project. So each instrument has its strengths and weaknesses, and most important to choose the appropriate technique for the particular sample and situation. that you're interested in. So I will stop talking there.